Okay, so it's 4. So let's start. Yeah, so as I was saying that today what we'll do is we'll go over the concepts of PCA and a little bit we'll discuss about PLSR, although it is not very popular because the actual algorithm in that is very complicated. I will try to discuss a simpler version. I'll try to explain a simpler version of that, and then we are going to discuss uh, briefly the support vector machine, the cart, and random forest. Those are all are also discussed briefly. It's just more of the examples because the working behind those particular algorithms are very complex. So if we go into the explanation, the technical explanation, it will take a lot of time. So we'll just touch over them and in before discussing these classification and regression, cart, random forest, and support vector machine, we'll do some programming exercise. So I will share the Jupyter Lab notebook with you guys, so you can also go through them at your own comfort. So one more thing is you're doing a course of machine learning. So if you guys are not comfortable with programming, then it is going to be a problem going forward. So I will suggest you guys to get comfortable with at least Python or R, and I will do the coding in Python Jupyter notebook. And if you are not comfortable with it, there are similar libraries in R also for the same. You can try in R. Okay, so let me just see something here, and we can start. Okay, so in the first lecture itself, I think when we were discussing about week 3, basic concept that will be discussed today is PCA, that is principal component analysis. All the other things are all secondary that come after this. So if you understand this, then you can understand the other problems. Yeah. So when we discussed in our first lecture itself something about methodology that when we are setting up the you know, machine learning model. So there was a step in which we were doing feature extraction or feature elimination. So like this PCA, PCR, PLSR are all basically that only. And there are two ways in which you can reduce the problem of overfitting in your model by eliminating by first is by eliminating some of the features that are related. So that is feature elimination. Basically what we do is we drop features that are uninformative or less informative. So we drop features that are less informative or non-unique, means can say it anyway. And what happens as a result of that is we lose some information. We lose some information. Why we lose some information when we have dropped less informative features? Can anyone tell me? Can anyone type it? See, basically what we why we are dropping this is because we found that two features were strongly correlated, you know, and that's why we dropped one of the features. So then why do we say that there will be loss of information? Okay, so there is a simple reason. I think the answer is too simple that no one wants to say. The simple reason behind this is they are not same features. They may be strongly correlated with each other, but they are still not same. They are different. They represent different things. So even if their covariance value is very high, or R square value is around 0.99, still there is a difference between the physical quantity that they are showing to us. Unless until you are your model is having weights in kg and pound, not as two features. I'm not talking about these things. I'm talking about, let's say, kg and age. So usually the weight increases with kg, sorry, weight increases with age. So still two things are representing different things. So if we drop one of these two, we are going to lose some information. Okay, so that is the drawback of feature elimination. So that's why we go for the second approach. In some cases, feature elimination will work if we don't want a very high accuracy, if we want to keep our life simple. But most common thing nowadays is feature extraction. So there are different methods for that, and one of the methods that we'll discuss is principal component analysis. In this thing, we create new independent variable that is a combination of the previous or the old independent variables. So x will have some features. This x is a matrix that is having x1 x2 as features. Now we create z that will have z1 z2 different features, which will be a combination of these old features. So z1 will be a combination of x1 x2 till xm, and z2 will be again some other combination like that. So we create new features that are combination of old independent features. Now here is the problem with this method. This method has a problem that now when you do this, you will lose the interpretability of your model, right? Because let's say you had your feature x, like your feature set x, where you had weight, then you had age, then you had gender. Let's not keep gender. Let's keep continuous values only. So let's say you had weight and age, right? Now when you do a linear combination of weight and age, what will you give the name to these new features? You cannot give that any feasible name, because let's say this z1 is some alpha 1 w plus alpha 2 age for a. Then what will you call this? You are forced to call this just some designate this just as a variable. Nothing, you cannot call it anything else, right? So you are losing kind of an interpretability. So when you plot it, you cannot show someone a plot and say, see, this my data set label y is increasing with weight or increasing with age, because now the plot that previously maybe was something like this even though it may be a nicer plot. Previously it was something like this. Even though it is maybe a nicer plot now, you cannot say this is age and this is weight. So we are actually increasing the complexity in our model. So that's why sir mentioned in the slides that you can go through again if you want to refresh that. uh, you have to decide when you want to use these kind of feature extraction tools. Okay, now so when we do these things, when we make our new set of features, you know, then we have to keep in mind that we have to try in such a way that uh, the new features are not linearly dependent. Why do I say this? See, previously we had x1, weight and age. So there might be some kind of, or let's add more variables. So let's remove this weight and age, and let's add more variables here. So let's have big X and then x1, then x2, then x3, then x4, right? So now after doing this operation of feature extraction, combining the all the features to make new features, there might be a case that in your this feature set you can actually represent x4 is equal to some alpha 1 x1 plus some alpha 2 x2 plus some alpha 3 x3. This should not be the case in your z. Otherwise, what's the point of doing all these things when we are still having a collinearity, multicollinearity in your features? So that is one of the things uh, which drives the process that we take to get these new features there. And I will ask you a question about this. I am giving you a hint now itself that none of these things should be linearly independent. And I'll ask you a question related to this in the coming slides. Okay, yeah. So one more thing that I will not be discussing in this session is I want you guys to be familiar very good, very nicely with eigenvalues and vectors. So how many of you are familiar with eigenvalues and vectors? Okay, so how many of you are not familiar with eigenvalues and eigenvectors? No one wants to answer. Okay, so see, I have taken a course in past semester, that is optimization methods for civil engineering, wherein I have explained in the first, I think first two lectures. One is 19 minutes and another one is I think 45 minutes or 50 minutes. In that, I have explained what is the physical significance of eigenvectors, eigenvalues, and matrix multiplication. So you can attend, you can listen to this class. Get You may not be able to fully understand this, but if you try to understand through those videos or some other videos, wherever you want to learn what is this physical significance of eigenvector or eigenvalues, or yeah, how do they work, what is this matrix multiplication actually doing to a vector, when you read all those things, then it is going to click very nicely with you. So you can be a part of this video, but you will absorb it even better when you know what is the difference, or what is eigenvalue or eigenvector, and what do matrix do to a vector when we do a matrix multiplication. That is very interesting. The first time I learned it, was in the Coursera course. I took maths of machine learning. In that, it was very interesting. Okay, so let's go forward without wasting any more time. Yeah, so we have discussed this feature elimination and feature extraction. Now let's discuss about PCA, the main focus of today's class. What are the steps? How do we get the principal component for our given features? Okay, so first of all, you get the data set, right? And you create a matrix X which has all the feature data set, right? The explanatory variables, that some terminologies sir has mentioned for the independent explanatory variables. So you give it that you data set for independent variable, and then y, small y, usually we represent it by small y, are the labels for the dependent variable. Since this is a supervised learning, so sorry, this is an unsupervised learning, but we are just for our simplicity to to show it nicely, we are going to use this. We are not going to use this in any of computation. Only for the plot we are going to use this. So one more important thing to note about PCA is it is unsupervised. Whenever an algorithm or any process does not involve the use of the labeled or dependent variable data, then we call it as unsupervised. So this PCA is unsupervised. Okay. Now we have X, our independent data set variable, which is having the features in columns x1, x2, x3, and so on. Wherein the number of columns, so if X has a dimension of n cross m, then m is the number of features and n is what? N is the number of data set. And what will be the dimension of y? It will be n cross 1, because how many ever data sets we have, that many labels we have. Okay, so when we have that, what should we do? One very important thing about PCA, that is principal component analysis, is that it is just a way to rotate your existing data. So now to represent this set of points, I need two variables, y and x, or to avoid confusion, let me call it as x2 and x1. But when I use PCA, I can rotate this data along this line, and then I don't need this x2 dash. Let me call this x1 dash and x2 dash. I can just use this x1 dash to get things done, because x2 dash is almost zero for all these things. So we have just rotated this to the x-axis, right? So basically PCA is doing that. And when you understand how this matrix multiplication and rotation works, you will realize that the most important thing to do before rotating or doing any kind of operation to a vector or a matrix is we have to center the data, right? So let's say I will explain to you how this works. See, what I showed earlier was a point set that was passing through the origin, but that will not be the case always. Let's say you have a point set like this, right? Now these are also having a strong collinearity between them. X2 and x1 are still collinear, right? Now what will you say? You will say that you rotate it to x1, and then you can avoid the x2. Rotate it to x1, now you avoid the x2. But whenever you are rotating a point, how much actually we have to rotate. So how do we calculate how much we have to rotate? We'll get this line, and then we are going to rotate this much, right? Do you all agree that we should rotate this much to all the points, because we are not going to rotate each and every point separately? We have to rotate all the points in one go. So we have to rotate it like with this angle. Yes or no? Okay. So no one wants to say. So we have to rotate with this angle. Now the thing is, you have to rotate this, but when you do this rotation, what it is going to do? It, since it is not passing through origin. Okay, let me. Since it is not passing through origin, something very weird is going to happen. It is going to rotate this, but no, by that angle, but not in the way you think. Let me show it to you approximately how it is going to look like. Now it has rotated the axis like by this much theta. Let's suppose that this was the theta that we needed. And what ends up happening is that you have a data set now. So these are the new, I'm trying to show that these are the new x2 dash and x1 dash, right? Now they should come on this x1, logically speaking, right? This is what we expect, but it is going to be like this, because it is going to rotate around the center. When we calculated theta, then we said that we have to rotate it around this much. So to avoid all these problems of calculating angle here, then transforming this angle to the origin angle by some degree, what we have to do is we have to center our data along the origin. What does that mean? You calculate the mean of x to x1, you calculate the mean of x2, and subtract from each of the points the mean of x1 and x2. And your data will now look like this. So now when you rotate it by this theta, your new data is going to align nicely with your x1, and most of your work is done. Okay. And on top of that, if you can do a scaling of the data, then it is going to be even better. You will not have to do a normalization of the eigenvectors in the process. So I'll just write it here: center the data plus scale the data. So each feature you have to do it separately. Okay. So this process is called standardization of data. How do we represent this mathematically? We write it as x new, or x scale, I like to write, is equal to x minus x mean divided by standard deviation of x. So you will have your new x1, your new x2, let's call them these things. Okay, this is one of the steps. Now, what next do we have? So now you have to calculate the covariance matrix. There might be some mistake in the slide, so so you don't need to be confused. Whenever you feel that there is a problem and you're not able to understand what is written in the slide, or it is contradictory, see, because we are also humans. The sir has made some slide that is, that is also made by some student or himself. So there may be some mistakes. So you can point those mistakes out uh, in the message or the NPTEL portal, or you can when you try to Google or try to search through the net. If you're not understanding any topic, then you will find the correct. So you have to get the covariance, calculate the covariance matrix. What is the covariance matrix? Covariance matrix is, you may remember this, it in the diagonal we will have covariance of x1 with x1, x2 with x2, and so on, xm with xm, and in here we'll have x1 with x2, and so on, x1 with xm, and here we'll have xm with x1. Yeah. So sorry. Yeah. So this is a matrix made up of the covariance values of one variable, one feature with another. Now, my question with you is, when we are actually doing the programming, so if you don't know the dimension of this covariance matrix before calculating itself, you will not be able to proceed. So, can anyone tell me what is the dimension of this covariance matrix? How many rows, how many columns? Come on, we have good amount of people. Can anyone give it a shot? No one? Okay. So I will give you a hint, and then after 1 second I will give you the answer. So that if you were trying to do this, then you will not be discouraged. So we are calculating covariance of one feature with another, and diagonal in the diagonal we are writing the covariance of that variable with that variable itself. So how many how many features we have? Actually, we have m features, right? And how many diagonal entries we can have? We can have m diagonal entries. So this will be, and on the top we will have feature 1 with all the m as the first row, and on the column we'll have feature 1 with all the m as the first column. So this is m, and this is m, and this is m. So it is a square matrix with dimension m cross m. When you do it in the coding Python, you will see that m rows. Oh, very good, Vishnu. Thank you. Yeah, so when you do it in the Python, sometimes because Python doesn't know that you are talking about feature or you're talking about which row is feature, when you are inputting the x, you can directly input this x matrix into that, and then you can calculate the covariance matrix. Life is easy in Python. So but it doesn't know which is actually your feature, what represents your feature or column. So you might have to give transpose and all. So you may see that your covariance matrix instead of n cross n, it is n cross n, or it is different because your x is the x matrix is n cross m. So in that case, you will have to give the transpose, and then you will get the correct, you know, answer. Yeah, so this covariance matrix is m cross m. Now, when you know this and you have found out this covariance matrix, then see, the next step is now to get the eigenvalues and eigenvectors of this covariance matrix. Just a refresher. How do we write what is the formula for covariance? Covariance formula is between x and y. If anyone needs any refresher, this is the covariance formula, right? Am I have I written anything wrong? I hope not. So this is the formula for covariance between x and y. Okay. This is so this will constitute one value of this matrix. Similarly, you have to calculate all. Okay, now when we have this covariance matrix, let's call it as COV underscore X, which is a M cross M matrix. Now we want the eigenvalues and eigenvectors. So this is a M cross M square matrix and also symmetric. So how many eigenvalues will it have? An M cross M matrix, symmetric matrix, how many eigenvalues it will have? So it will have the principle, like the method we used to calculate the eigenvalues was, we made the determinant of of one matrix which was obtained by this to 0. This is the way to where this lambda, actually let me keep this as lambda itself. Lambda is the eigenvalue. So when we have, let me show you that, let's say this is a 3 by 3 A matrix, then we need an identity matrix also 3 by uh, 3 by 3, which is just lambda, let's keep it outside, 1 1 1 0 0 0. I hope you know what is an identity matrix. And then we'll get some matrix after doing the subtraction, and we have to get the determinant of that matrix 0. So when you do this, you will notice that you will find yourselves having a cubic polynomial in lambda, and it will have three roots. So the order of the square matrix is equal to the number of eigenvalues that you will get for that square matrix. So for this M by M covariance matrix, we will have M eigenvalues, and each eigenvalue will be separate because this is a symmetric matrix. So this is also one of the properties that you can check. And each corresponding eigenvalue will have a eigenvector. So this V is also something similar, shares the same dimension as that of the covariance matrix. So it will have V1, V2, Vm. So V1 will correspond to lambda 1, V2 will correspond to lambda 2, and Vm will correspond to lambda m. Okay, and the column entries will include the eigen vectors. Yeah. Now we are going to use these eigenvectors to transform our uh, existing dataset features into the new dataset features. Let me come to that question, but before that, there is one more important thing that I wanted to discuss is that these eigenvalues that we get, these m eigenvalues that we get, these are actually, so in the session, in the presentation, I don't know if you noticed or not, but I thought that it is a point worth mentioning again. That is, we have to arrange these eigenvalues in descending order. Did you have not done that? Then all these methods are not going to work out. Whatever I'm saying, these things may not necessarily be true. So keep in mind that the precursor to this statement is that you have centered and scaled your data. Okay, so that is a point to remember. Then we arrange the lambda in decreasing order or descending order. Now, when we do that, let's say lambda 2 was greater than lambda 1. So this vector, this matrix of eigenvectors is also going to be modified. So V2 will come first, V1 will go later, and then so on. Okay, this is your matrix of eigenvector. And what you do, this is an also M cross M. Now you want a new set of features, that is, let's call them principal components, so PC. And for now, just after doing the operation, they will share the same dimension as your actual X. So they will be N cross M only. So to do that, we have to do X matrix multiplication with V. So n cross m multiply m cross m. You will get a matrix that is n cross m, because these two will cancel each other. And after that, when you have this PC, you will see that this is PC1, which explains the highest variance, then PC2, little less, PC3, you know. And you can check all these things using your scree plot, using your loading rate, or uh, the biplot, or several plots are there. You can check it using any of the things. Okay, so we'll do the programming exercise. But before that, we'll discuss a little bit about this PLSR, that is partial least square regression. Okay, so I want to ask one question. I'm forgetting. Yeah, yes. So when we are transforming our existing data set, that is n cross m, can anyone tell me? See, I gave you a hint in earlier. Can anyone tell me why do we use these eigenvectors only to do that? What unique nature do eigenvectors possess that I want to use them to transform my existing data set? I'll be very happy if anyone can answer that, or even if you try to answer that, then it means that you will get it eventually, if not now. Try to recall the hint that I gave earlier. What do we want in our new data set, new feature data set? Sorry. Okay. See, I mentioned that in my new data set, I don't want transform into descending order. That is true. That is true, Vishnu Kanu. That is true. That for that we use eigen values, and we use the eigen values to uh, swap the columns of our eigenvector to get a nice eigenvector. Also, if when you have done this scaling and centering, you don't need to do that. But in some cases, you need to normalize this eigenvector before using. What normalize means is you have to get the eigenvector, let's say v2, and divide it by the magnitude of the eigenvector. That is nothing but sum of sum of square of each elements and the square root. So v2 1 square plus v2 2 square plus so on, vm sorry v2 m square. So you can check actually what is normalization. We have to do this for each of the column. Okay, so the actual answer, the reason that we are trying to do this is very interesting. Your vectors possess a very nice property, that if your eigenvalues are different, right, then the eigenvectors corresponding to these eigenvalues are linearly independent. What does that mean? That means you cannot write any of the eigenvectors, let's say Vm, as a linear combination of V1, V2, V3 till Vm minus 1. You cannot write Vm in terms of any of the other eigenvectors. And that is the property that we were looking for in our principal component data, right? So that is the only reason we use this eigenvectors, because they provide us that property. When you multiply these features with this eigenvector, then it is going to transform it into the data which we want, and it will give that property that we want. Is that clear? See, eigenvalues and eigenvectors are fascinating. Their use in machine learning is endless. The more you know them, the better you get in machine learning. Okay, so yeah, so now we have Z, and then you can, as I said, that you can decide which one to choose, with PC1, PC2, which one to choose. Just remember this. Let me show it with an example. Let's say this is our eigenvector a 2 by 2, a b c d. This is v1 and this is v2, and you actually multiplied your x with it, and let's say x also is having x1 x2, because here there are two, so it will have to be two features, and you have some entries. Then your z1 z2, what will be your z1? Can anyone tell me, in terms of mathematical expression, what is z1 equal to? Don't worry about the whole thing, don't get scared by the whole thing, just look at the first row and tell me what is this these two first values of the z1 and z2 equal to. I hope you are familiar with matrix multiplication. If you are, then you should be able to tell this. A B, do we not multiply anything? Let's say that I am calling these as x1 1 and x2 1, x1 2 and x2 2. Now what will you write it as, Vishnu? Just you need to multiply some things with some things. Rows into columns, then addition, something. Uh, is, is anything clicking? I don't know if you are typing or not, so I'll just go ahead and tell the answer. Okay, okay. So yeah, so Z1 is actually x1 into A plus x2 into B, and Z2 is x1 into C plus x2 into D. Just look at it. See, x1, sorry, x1 into A plus x2 into B, right? And then for the next one, for the next column, x1 into C plus x2 into D. So I'm writing it in general. So this whole thing I have written it here. Okay, for some reason my internet was disconnected. My God, I hope. Okay, it came back. Yeah. Okay. So that's the answer for that. So whenever you are see now, like you use this to fit a parameter. No, now your y is actually, what you did was, you, instead of x1 x2, you chose z1 or z2, and you got z1 and z2, and you decided to keep only the pc1, that is z1, and you got a expression that y is equal to a z1 plus b, that is the slope and intercept. What is this mean? That y is equal to a into whatever your eigenvalue entries were, a x1 plus, oh, so let's not call this a, Let's call this beta 1 and beta naught. Bx2 plus beta naught. So your final expression will look like this: a beta 1 x1 plus beta 1 bx2 plus beta naught. Remember that this will be your final expression, because you need to get final expression in terms of the original features that you have. Okay, so we have this. And while you are at it, uh, since we did the scaling and centering also, so better if you x1 was what? X1 was x minus x mu by sigma. So if you replace x1, if you put it here, like in the place of x1 this, then it will be better. It will be exact relation that you want. So this is all about PCA, and then in the end, I discussed little bit this thing, that how you are going to use this PCA in your linear regression. That is only PCR, that is principal component regression. It is only how you use the PCA in your linear regression, that is principal component regression. Okay, now let's discuss a little bit about PLSR. Frankly speaking, this is a topic which is a little bit complicated, because if you you will not be able to code it very easily without using a very complex a looped kind of program, like an iterative kind of process. So I will just describe one of the iterative process to do this. That is simpler, very easy to understand. So we have partial least square regression. Before we discuss about this, why do we even need this? If you have gone through the lecture, then you should be able to answer. Why do we need this partial least square regression? Okay, so what we did in PCA or PCR was that we identified a feature, a principal component that explained, or one or two principal components that explained the maximum variability in our data. So if our data was something like this, then this was the direction of our principal component. And when we transformed the data accordingly, we got this data as our principal component. But all these things that we are doing here, we are doing it only for the independent data set, only for the x. We never used y here. So even though this transformed data set, that is PC1, is able to explain the variability in the input, it is not necessary that it is actually going to explain the variability in the output also. Usually it will do, but as an assumption, or in some very complex situations, we can say that it is not necessary that this PC1, that is the basic principle that we use to determine this, that was that it is going to explain the maximum variability in the input. It is not necessary that it is going to explain the variability in the output also. Output is what? Output is y, the label. So hence comes the partial least square regression, because it is going to use y, that is the label, that is the dependent variable, to decide on these values a and b. These are not just going to be eigenvectors or eigenvalues anymore. So it is going to use the y also to decide on these values a b, to get a combination of the features such that it explains the variability in x1 and x2 also, and in y also. So it is using the label or the dependent variable. So we cannot call this now, we cannot call this as unsupervised learning. This is now a supervised learning. Okay. And why do we call this as partial least square? The reason we call this as partial least square is simply because, let's say this, you have y is equal to, yeah, you have this kind of, this is your y, this is your x1, this is your x2, and you have some features here. What you will do is you will get LV1. Sir called it as uh, can anyone remind me? I am not able to recall what names are used for this. What was it? Latent something, right? Latent source, or well, let's call it as latent source. I think it was latent source. So we will generate a latent source as a combination of x1 and x2, such that it is able to explain the variability in x1 and x2, at the same time y also. And one and we will use this. So let's call this LV1, alpha 1 x1 plus alpha 2 x2. One important, when you do the derivation or you go through the basic principle of this PLSR, then you will see that there is a relation between alpha 1 square plus alpha 2 square is equal to 1. The same relationship exists here also in our PCA. Why it exists is, we had a normalized matrix of eigenvectors. Normalized means the sum of the squares of each eigenvector is 1. So a square plus b square is 1, c square plus d square is 1. So that same principle or that same condition exists here also. So you can actually replace one of these alphas, and you can write it as, let's say if I want to write it as a function of alpha 1, then I can write it as this, in this fashion. So now it is a function of alpha 1, our latent source, LV1. Now what I do, I say that okay, this is my LV1, and I assume some value of alpha 1, let's say 0.3, and I calculate the value of LV1 corresponding to the x1 and x2, because I will know the value of x1 and x2 and y, but I will not know the value of LV1. So I will use this assumed value of alpha 1 and calculate using this expression the value of each LV1. When I do that, after doing that, I'm explaining the basic how you go through this. After calculating the LV1 and having y also, you will calculate the covariance between LV1 and Y. See, what we want to do, we want to get a latent source or a new variable that is able to explain the variability in Y also, right? So why don't we just calculate the covariance of Y with that variable? When we do that, we will get some value. Now you change your alpha 1 and then calculate the LV1 again and calculate the covariance of alpha 1 dash with the Y again. If it increases, then you keep on increasing your alpha 1, and you have to actually set up a plot of the covariance L alpha 1, and you will see that it will make some kind of a polynomial or some kind of a nice polynomial. Most probably it will be this kind of polynomial for two variable, and you will see that this for some particular value of alpha 1 you are getting the maximum covariance between the latent source and your alpha 1, and then you choose that particular value of alpha to get the latent variable 1. Okay, and so this is the process, like this is how you do it. Then final expression, when you are going to write, you will write it as this only: beta naught plus beta 1 LV1. In place of LV1 you will write this combination of alpha 1 alpha 2 x1 x2. So in the last expression is not going to be very different from what we saw in the PC. Okay, but here is the thing: why do we call this as a partial least square? The reason why we call this as partial is because if you see this PCA, what did we do? We calculated the covariance with all the transformed features. So we started with n cross m, and we in the end also we had n cross m. Then in the like later on we dropped some of the variables and did the linear regression. But here in the starting itself we have not considered the another variable LV2. We cannot do that because in this case we are going to end up with the same expression, right? What how do we write LV2? Same thing we have to write. Instead of alpha we can use beta 1 x1 plus beta 2 x2. But when you do this computation you will find out that beta 1 and alpha 1, let me not call this beta, otherwise we will get confused with this thing. We may get confused with this beta. Let me call this as gamma. So if we were to write gamma 1 x1 plus gamma 2 x2, then you will see that gamma 1 will come equal to alpha 1. So there's no point in writing LV2 when we are using this particular methodology. So that is why, since we are reducing the number of variables here, instead of estimating, let's say here, instead of estimating one more beta 2 LV2, and then later on deciding whether we want it or not, we are just not we don't even care about that. Sorry. So that's why we call this as partial least square, because least square comes from this covariance. Because how do we calculate this covariance? Kind of represents the least square sum, right? This least square comes from there, and partial comes from us not actually predicting the other variable, the other latent source. This is how this name came. Okay, so this is how, if you want to, very the like the simplest way you can code this partial least square regression. The thing that sir explained, I have a PDF. It is very complicated to understand, and you don't actually need to understand that at this level. You can just use inbuilt packages for that, because it is, as I said, it is an iterative process. But I just wanted to explain you how basically what goes in behind the scenes. Okay, so now what I want to do is I want to show a programming part of PCA, so that the class becomes a little interesting. Because frankly, I thought there will be some programming assignments or something in this course, but since they were not there, it's a little difficult for me to keep my enthusiasm, and I can imagine it might be the same for you guys. So I'm going to uh, do some programming assignments. Sorry, some programming exercise, and you can look at it. You can try it. You may not. It may not be wise to follow, because I have written the codes and I'm just going to explain them. But I will share the Jupyter Lab notebook. You can copy paste it in your lab notebook, or you can use that lab notebook to go through it. So let me just. How do I do this? So I have to remove. I have to share my screen, laptop screen instead of tab. Okay, so okay. Now let's go here. And what is happened? I am not able to change that. Okay, just a minute, guys. I may have to rejoin the meeting. Just give me a second. Yes. So my screen, I'm not yet shared my screen. Screen one is this. My screen is visible, right? Can anyone tell? I think it is visible. Okay, thank you. Thank you. It is recording also. Yeah. Okay, so let me explain this code. Uh, NumPy, so we are just importing some packages that do most of the work in the backend, so that we don't have to do manually everything. NumPy is the scientific library that is a must for machine learning, and matplotlib.pyplot is just used for plotting. So we import these things. So once you enter in your cell in the Jupyter Lab notebook, we press Shift Enter, and star comes here. That means it is executing. After it shows a number, that means it has executed. Now then we import the data and inspect how many features we have. So I will ask you guys how many features we have and how many data sets we have. So for that, for machine learning, there is a very nice library, scikit-learn, and we are using scikit-learn.dataset to import some dataset that is stored in the load vine. So some vine output and some dataset for the vine. Again, shift enter, and we see that the shape of the x, that is the matrix that is containing all the features, is 178 cross 13, and shape of y, that is the label, is 178. Whenever it is 178 cross 1, it cross comma nothing, that means it is 1. Just problem with NumPy or Python, that it doesn't, whenever it is 1, then it wants to remove that 1 and wants to keep it as just 178 individual numbers instead of an array. Okay. Can you tell me how many features we have? What is the M in this X? And what is the N? How many data sets we have? If you have written anything that when I was telling, then you should be able to answer this question. Let me drink water. Why don't you guys think and tell me the answer for this? Sorry. No one? That's surprising. So, as I told, that at least why should have been able to tell me that why has the label or the output for each of the data set. Oh, okay. So Vishnu tried. Answer is not correct, Vishnu. It is swapped, but still, thanks. At least Vishnu has tried. So see, I said that y will have output for each of the data sets, right? So 13 is the number of features, and 178 times we have different value of 13 features, and then when they combine, then we have 178 times what is the resultant y corresponding to that. So if just to show you, it might not be very friendly to see, but this is how it will look like. These are all, the rows are 178 and these columns are 13. So x1, x2, x3, x4, x5, and so on, x13. Okay. Now let's visualize. Since we have 13, and in the plot, in the figure, we cannot actually represent 13 dimensions. Till now we are only limited to 3D space visualization, and in some cases 4D people have tried, but it will be difficult for us to do. So we are only going to see three features: x1, x2, x3. One thing to know about Python is that the first index is always taken as 0. So when I say x on square bracket colon comma 0, I am talking about this first column. Okay. So colon means all the row, and 0 means first column. Here colon means all the row, and 1 means second column. Or maybe it is difficult to see in some small screen. It might be difficult. Let me, how do I increase this view? Uh, okay, let me just increase the window size itself. Okay, I hope it is better to see now. Yeah, so I am plotting x, x1, x2, and x3. So it is a scatter plot, 3D scatter plot. And how do I represent the y in that? Since I know that actually this is a classification problem, so y will have some kind of fixed values. In this case, 3. So I will change the color of these scatter points based on the value of y. So this is how it will look like. Plot looks like this. See, there are three values of variations in color, and we have three variables: x1, x2, and x3. Okay, I hope this is visible. Just a visualization. Now we do the centering and scaling. So the matrix X stores the value of the features without any kind of centering and scaling. Now we'll do the centering and scaling. So what do I do? First, I calculate the mean of the all the features in one go. So for that, I use my NumPy library that I imported earlier. And what do I do? Since I have this X as a matrix, I have to use some syntaxes so that the mean that it is taking in this direction. So first mean should be the mean of x1 should be taken around this, the mean of x2 should be taken around this and around this. So for that I have to use a syntax x is equal to 0. So you calculate the mean using this command for the x and keep the axis as 0. Keep dimension true is just something that is not important as of now, but just keep it when you are trying to code it. Similarly, I will calculate the standard deviation. For that, we have np dot standard deviation, and then I scale it as I showed the wrote the formula uh, in the tab x minus x mean divided by standard deviation. And then I just want to print the shape, and I want to make sure that I have the same shape, that is 178 comma 13, and we have, and I will plot it. So after we plot, what you will see is that you see x1 is varying from 11 to 15, x2 from 1 to 6, x3 from 1.5 to 3.25. After we do this centering and scaling, the center of each of these variables is going to be 0. So when we do this operation in any variable, what happens, what we end up doing is we make its standard deviation, the new set of values that we get, we'll have a mean of 0 and a standard deviation of 1. So let me show you. So I am storing it in x underscore scale, and I am plotting the first three features again for that. Sorry, so 0, I made a mistake here. 0, 1, 2. That means first feature, second feature, third feature. And again, the color is going to be depicted by the value stored in the label. First, I printed the shape of this x underscore scale. It is same, so uh, I'm sure that my calculations are correct here. And you see, after I have done the centering and scaling, the center value is 0 here, 0 here, and 0 here. So like when I say center, it doesn't needs to be center in the figure. It is the mean. Mean is now 0, which may not be able to, you may not be able to visualize it, but just take my word for it. The mean is now 0. We can prove it mathematically also. Nothing much has changed though. The variation is same. But you see, you remember Sir's figures. We are also going to see a nice figure like that, in which we will see green points going separately, yellow going separately, and these purple points going separately. Okay, now we have come to the main calculation part of our thing. We want to calculate the covariance matrix. So a very nice thing if you know coding. See, we don't even have to calculate we don't have to calculate the covariance each time. Otherwise, just imagine 13 times 13. The size of this. What is the size of this? What will be the size of the covariance matrix in this case? Can anyone tell me? 13 cross 13. Nice. So the size of this covariance matrix is going to be 13 cross 13. And if we were to do it one by one, just 13 into 13, 169 times we will have to calculate. But thanks to Python and thanks to the NumPy library, I can just input the matrix inside this np.covariance, and it is going to give me the covariance matrix itself. Now, as I was saying earlier, see this x scale is a matrix. Now this function np.covariance doesn't know whether the row I have to calculate the features are stored in column or they are stored in this uh, rows. So we have to see, just check it what is the size of this covariance matrix, and then we will be able to, if we have to give transpose, then we can give transpose. So let me just show you that if I had not put this uh, transpose here, this dot p means transpose, then what would have been the size of our covariance matrix? So see, if I had not given transpose, the size of our covariance matrix would have been 178 cross 178. But when I give the transpose and it nicely aligns with the data, then you will see that we have a covariance matrix of size 13 cross 13. So to get the size for when we have a numpy array or a matrix, we can use the command dot shape in the end of whatever that matrix is. Variables. Okay. So we have our covariance matrix. Now we are going to use this covariance matrix to calculate the eigenvalues and eigenvectors. For that also we can do that in one line itself. If you'll go through my old video that I was saying, in which I have explained the eigenvalues and eigenvectors for my previous course, you can find it in the YouTube channel. You will see that it is not that easy to manually calculate the eigenvalues and eigenvectors. Solving a cubic function is difficult in itself, but when it comes to solving a 13 degree, because here we are going to get 13 eigenvalues and then 13 set of eigenvectors, then manually doing that, it's just a nightmare. So then we can again use our NumPy library, and we have in that library we have linear algebra tool, and in that we have eigen function, which in which if you give this covariance matrix, it is going to give you the eigenvalue in W, and matrix V, that will have eigenvectors corresponding to these W values stacked in column. So let me just show you how it will look like. One by one we'll look at it, because first was the size of the shape. I can remove it. I don't want to see that anymore. Now these are the eigenvalues, 13 eigenvalues, 13 unique eigenvalues that we have for our square matrix, that is covariance matrix. Right? Nicely we can see 13. And similarly for each of these eigenvalues, we will have eigenvectors also. So see, we have now here, you can see I gave print v instead of print w. So we have eigenvectors. We have 13 eigenvectors. This is one eigenvector for the first eigenvalue. This is for second. This is for third, and so on. Now we have to arrange, as I was saying, these eigenvalues, and we will show also. We will show why I was saying that these eigenvalues represent the covariance of the transformed data, and we want the highest covariance to come first. So we have to arrange this eigen values and eigenvectors also in the decreasing order. So I use this particular uh, three lines to do that. It can be done. There may be a way to do this more simply, but it was simpler for me. So I get the index for the decreasing order of the eigenvalues, and I put in the values inside this V to sort the columns, and I just simply put the indices inside the W to get the W sorted. So let me just run it and print the W sorted, so that it is confirmed that we are doing it correctly. See, you can see nicely that the W sorted, when printed, it is in decreasing order: 4.27, 2.11, 2.1.45, and the last one is the smallest one. Right? And similarly, in this same similar order, the eigenvector corresponding to this first one, to 4.73, will be in the first column of V sorted, and corresponding to 2.511 will be in the second column. And the final step that we discussed was, we have to transform our data X scale into the PC data by using this matrix of eigenvectors. So we use this PC sorted, actually, sorry, P sorted, and we do a matrix multiplication between between X scale and V sorted, and we get our uh, uh, data of we get our transform data. So this np.matmul is used to do the matrix multiplication between these two. So this is the size of this is 178 cross 13. The size of this is 13 cross 13, and the final result we'll get will be 178 cross 13. Let me just type it here. You can see 178 cross 13. Now we'll use this and we'll show you how the data looks like. Okay. This is how the data looks like, but you may not be able to clearly say here that the data is, that is separated. We are seeing some separation, but not very clearly, right? So let me just change the angle and show you that the data is indeed separated nicely, right? So I have plotted correctly here. Yeah, so when you do the previously, if you see these plots here, if you use the same if you use the same code, same view angle, you will see that you will not be able to see much of the variation on top here. Just a minute. Centering and skewing of the data. Not these are somewhat combined, but now if you see here, we have some kind of a distribution between the data. Now we can do this by this process, or what we can do is we can use an inbuilt package. Okay, oh, so after that we have this also. So this was the score plot that sir discussed, and other plot, that is the scree plot, we can also plot that. That is just the bar graph of the eigenvalues, that is the sorted eigenvalues. So it will look like this. Let me just zoom out a little bit. This will be the bar graph of the sorted value. So you can see this is the eigenvalue, and this is nothing but actually the covariance of the transformed matrix. So yeah, maybe I should show that. So this is our transformed matrix, right? So let me just show you that what is the covariance of our transformed matrix, and you can compare that to the eigenvalues, the sorted eigenvalues. So covariance one, and then we can use the PC data, and I can print it and remove the shape. Okay, give me a moment. I just need to check something first. Yeah, we have that right here. Okay, so there might be a mistake in this. I'll look at it and update it later on, but you can remember that one, and you can use the eigenvalues to see that sir was saying that we don't want any eigenvalue less than one in our principal component. So you can use that to. So this is the first principal component, the second one, third one, and then we only want these three principal components to be there in our linear regression, or you can set up even a lower ones. So from 0 to 12, you have here 13 principal components, and you can choose whichever you want in the end, how many ever you want in the end. Now we can avoid doing all these things, as I made some kind of mistake here. You can avoid doing all these mistakes by using the inbuilt package that I will suggest, because not everything we can code. So by using an inbuilt package that is more robust to all the susceptible, not susceptible to errors here. to do this kind of operation. So this scikit-learn.decomposition will have a package called PCA. You can use that, and just you have to do one thing: this X transform is equal to PCA dot fit transform and X. Whatever your features was, you can just put it in, and you will get a matrix XT that will have the shape, same shape, 178 cross 13. And not sure what for once, I'll just show this same shape, but these are all transformed now, right? So you can use this, and now we'll see the plot. So here's the problem with this plot. This plot doesn't look as good as the plot that we saw when we did our own calculation. Why is that? So the reason behind that is we have given here x, and what is the main and very crucial step that we have forgotten when we directly give the x here? Coding font is too small. Oh, sorry, just I didn't see that. So yeah. Anyhow, I'll be sharing these things so you can look at it personally. Maybe. Yeah. So why? Can anyone tell me what is the crucial step that we have missed when we have just directly given our data set without any pre-processing into this inbuilt function of PCA.fit transform? Once one crucial thing we have missed here, and I had put very strong emphasis on that. Yes, Justin has correctly said that we have missed the scaling and also centering. Scaling and centering, that is the standardization. That's why we got like this. Now we have a data, fortunately, that is scaled and centered. Now let's use that and see what happens. So when you do that, you see you got a nice distribution similar to what we got. The color may be a little bit different, and the way they are doing this transformation might be a little bit different. That's why I am saying that we should use the inbuilt packages, but we can see some kind of distribution or categorization of these yellow, green, and purple dots. So that is why we should use this PCA, because then we don't have to go back and check again what are the problems in our code or what is going on. Okay, so this is for PCA. Similarly, we have a library for PLSR regression. So I have given this library here, and I want you guys to, if you want to, you can try it. You just have to Google what is the input for PLSR. It will be just another one line. I want you to do it yourself. It will be just another one line, and then I want you to show me. If it's not forcing you, you can give it a shot so that it will be more familiar with you. Because I know if it is just theory, then it's not very motivating to do any kind of work. Yeah, so you can do this. Okay, so that is all for these two things. Let's just briefly discuss about the other uh, topic that was discussed in class. Other things. Let me stop sharing my screen here, and I'll share from my tab again. Okay, I think yeah, my screen is visible. Yeah. Yeah. Okay. So now, not very these topics that we are going to discuss now. They are not very commonly explained. Just we all use them in one way or another in machine learning. Some people use support vector machine, the card. I forget the full form of this card. Can anyone tell me? Can anyone remind me the full form of cart? What was it? Classification and regression tree. Yeah, classification and regression tree. So I hope you have gone through the video because there is nothing much to basically explain here because it is a complex algorithm and I don't want to get into the detail of this thing. I will though share you this common thing between cart and support vector machine. Why I want to say that why this support vector machine is better than cart. Why I feel like that SVM is better than cart. What is the basic principle of SVM? It wants to give us a plane or a line that follows a path such that you know it has maximum distance from nearest point. So just imagine that you have this kind of data set. So your support vector machine is going to be able to draw a line that is something like this, and you have a nice division of the data. But what do you think your uh, cart will do? What kind of line will it give us? The cart, the at best, it is going to give us this line, right? Because we have seen in the so this is x1 and this is x2. This is x1 and this is x2. We have seen in the tree, the classification and regression tree, that it works just by having a x greater than 0 or x, let's say this is 10, x greater than 10 or x less than 10 kind of approach. It doesn't fit a line, it is going to fit just one line, these two boxes, and if you have done correctly, then you will be able to you will be able to uh, get this kind of classification. If you have done some kind of overfitting, then you may be there is a way. If you have done some kind of overfitting which is very inefficient, then you may be able to get something like this. In that case, this might be your classification. So this is one class, this is another, this might be one of the classifications, but still it is not as good as this SVM here. Yeah, so is there any doubt in cart, SVM or random forest? Because I don't want to spend more time on these things. I don't feel like they are as important as this PCA. If you guys have any doubt, then you can ask me. I can try to answer those. Okay, just one question. Support vector machine, is it unsupervised or supervised? If you guys are not asking, then let me ask this question. Support vector machine, is it unsupervised or supervised? What does it do? Supervised. Very good. So if though for those who are not able to understand, how is it actually making this line? See, the it is making this line by knowing that this point here, this this point here is actually a red point, and this point here is a green point. Only for the distance purpose, it is using the feature values x1 and x2, but it knows that these points are the points that I have to separate. So it is actually accessing the y label to get that information. That's why we call it as supervised learning. It will find the suitable line with maximum distance with support vectors. Correct. Very good. Yeah. And then regular forest is nothing but the same cart, but a lot of carts clubbed together, and the same as we discussed in the last, I think, week 2 session, the ensemble models, bootstrapping, and like doing a repetitive or replacement sampling, creating a large number of samples with limited amount of data, and then training each week separate week models, and then using majority for classification and average for linear regression. So kind of making a ensemble model to, which is better than most of the single or individual better models also. Yeah. So if there is no question, then I'll end the session for here today, because I want you guys to try out that PLSR, because it is fresh now. You may be able to try it before it's too late.